Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and now we'll be talking about in this presentation the methods which are used for surface modification, and one category of the methods like the modification of the surfaces without changing the chemical composition, that is what we will be talking about. But before going into the methods used for modification, I'll talk a little bit also about the classification of the surface modification techniques, wherein some kind of the coating or the layer is developed onto the surface. So these methods involve like the melting is one. Melting based methods are where weld surfacing or weld overlaying is carried out, or the laser cladding also forms in this category, where the heat of energy of the laser is used for developing a cladding or of the or a layer. Hot dipping is the one of the methods where the different methods are used for applying the coatings or applying the coatings for variety of purposes, like the zinc coating, lead and tin coating, and then aluminum coating and copper coating. So these are used like chromium coating for improved aesthetic regions and improved corrosion resistance by aluminum, and the zinc is also used for corrosion resistance coating methods, corrosion resistance applications. Then we have electrolysis based methods. There are two broad categories of the electrolysis based methods. One where is electroplating is carried out, and another is electroless coating is carried out. Electroless coating is carried out. So in electroless coating, basically nickel, phosphorus and nickel boron kind of the compounds are deposited. Coatings of these are deposited mainly for improved wear resistance applications, while in the plating, variety of the materials are deposited, like chromium and the nickel coatings are deposited through electroplating for the aesthetic reasons, aesthetic improvement. Then hard chrome coating, coatings are applied for improved wear resistance applications. Then electroplating of the copper and the silver is applied for improved electrical conductivity, and then there is a layer of like the cadmium and zinc for corrosion resistance applications. So there are different types of the materials which are applied onto the surface through the electrolysis based like electroplating or electroless coating methods. Then there are mechanical methods, where in roll bonding is one of the methods where the between the two rolls, the substrate and the coating material, they are forced to pass through the rollers so that the bonding between the two happens. This is especially used when the two materials in the fusion state do not have the good compatibility, and then explosive bonding is another method. So the mechanical methods are used for those situations where the coatings to be applied or the material to be applied at the surface do not have compatibility with the surface. Since the surface modification or the surface engineering primarily involves the modifying the surface characteristics, so we need to see what the surface characteristics are important. There are two aspects related with the surface features and surface properties. One is the surface roughness, which is primarily seen in terms of the RA, central line average value, and another is the subsurface characteristics, subsurface features. So their subsurface features include variety of the zones. Here the one zone which is just at the surface of very few angstrom thickness, having the absorbed gases, moisture, etc. Thereafter there is another layer which comprises basically oxides and nitrites due to the interaction of the substrate with the atmospheric gases. Then we have the very deformed layer produced by the like in course of the machining. So a deformed layer which is like mostly in form of the mechanical mixed layer or very badly damaged layer will be having the effect of work hardening. Any surface basically will have this kind of the components which is produced through the manufacturing process followed by machining. Then there will be another zone having the deformed grain structure. Here the grain structure is badly modified and the damaged in the deformed layer, but here the grain structure is deformed. So grain structure is recognizable, but it is in deformed state, like elongated in one particular direction, and thereafter we have the substrate or the base material, or we can say undeformed or unaffected region. So any surface will have these 5 types of the zones: 1, 2, 3, 4 and 5 unaffected zone. So in the surface modification, either 2 or 3 zones are altered for modification of the surfaces. So few of these zones are modified during the surface engineering or the surface modification for improved performance. So one of the techniques which is there are so many techniques as we have talked about the surface modification, or which can be used for the surface modification. Now we will see what are the things which are falling within the scope of the techniques, and up to what extent surface modification is possible through these techniques. So since the techniques are very wide in range, say for example the thickness, the depth up to which surfaces can be modified can vary significantly, which may be in this form like 0.0001, 0.0001, then 0.01, 0.01, 0.11, 10 and 100. It's in mm. So this is about the thickness of the component which can be modified by the different processes. So if we see the processes, the thinnest layer which can be modified is by the ion implantation. So here is the ion implantation. This is one, and the thickest layers which can be developed by the like 1 to like 40 to 50, 1 to like say 40 to 50 mm thickness layer can be applied through the weld surfacing. So between this we have very wide range of the processes with the varying capability to modify the surfaces up to the different depth. This is what we can see from this diagram also. So what we can see here, like the thinnest surface modification is possible by the process A, that is ion implantation, then process B and C having the like 0.01 to 0.01 depth of modification, that is physical vapor deposition and chemical vapor deposition. Then process D is for electrolyte plating, electroless plating for E, and hot dipping is like galvanizing, aluminizing, etc. For process F, it offers very greater thickness like 0.01 to 1, about 1 mm. And then laser surface alloying, laser transformation hardening like induction hardening, flame hardening, etc. These offer like G and H processes, like this is for transformation hardening, G is for laser alloying and H is for the transformation hardening. I for mechanical working, it is having very wider range depending upon the process which is being used. Then J is for laser nitriding, and like we can see here the N is for the friction surfacing and O is for the weld overlays. So thickest layers are possible, thickest layer of surface modification is possible through the weld surfacing, and thinnest one is for the ion implantation. In ion implantation, this is the diagram which shows that the 5 different zones. The top zone absorbed gases and moisture, second zone is oxide, third zone is the deformed layer, fourth zone is the deformed microstructure, and fourth is the unaffected base metal. So now if we see the different, there are wide range of the processes which can modify the surfaces up to the different depths. But so depending upon the purpose of the application for which the surface needs to be modified, the suitable process is selected so that we have the modified surfaces up to the required depth, or the required depth of the modified surfaces is made available. So there is a systematic approach for developing a coating or modifying the surfaces of a component so that we get the desired combination of the properties for a given application, and therefore entire surface engineering or surface modification approach has the 4 different branches, we can say, or 4 different steps which need to be followed before executing any kind of surface engineering. The first one is the design of the surface modification. Means design means the kind of properties. After the surface modification, what properties we are looking for in terms of the hardness or optical properties or electrical resistivity or thermal conductivity, any property whatever is required for the improved functionality and improved life and improved performance of the component. So surface needs to be modified accordingly. So we need to in light of the requirements, we first identify that what material, what process, what phases we need to have at the surface so that we can have the desired combination of the properties for the improved functionality of the component. So in design, basically the material, processes and etc. are identified so that we can achieve the desired surface properties. So the first stage is to design what we should have in order to achieve the desired set of the properties so the functionality can be improved. Second one is the developing. As per the design, go for it, means from the design we have identified the material A is to be applied, and then using process B, then let's apply that material A using process B. So this is the second is the development phase. Development of the modified surfaces, whether it is through the laser hardening or flame hardening or burnishing or carburizing or ion implantation, any method we take. So as per the purpose, we select suitable material, a suitable process so that the surface is modified. Once the surface is modified, the next step is to investigate the modified surfaces. Investigate or characterize using suitable set of the NDT and DT techniques, destructive non-destructive techniques. It is established whether the modified surfaces are having the required set of the properties or not, and once if that is established, then we will go for applying or application. It will be applied onto the real component so that it can be made for the purpose for which it was designed. So the fourth step is the putting the approach which has been developed into the application. So the first step is design, second is development, third is investigation and checking the suitability of the material. So NDT will tell us up to what extent it will be meeting the requirements, and then if it is suitable, then it will be put into the real components for the required purpose. So these are the 4 components which will be defining the scope of the surface engineering. So basically we need to look for the design as well as the development. Basically we will be talking about the different modification approaches need to be used for modification of the surfaces, because from the design aspect, maybe it is required to be looked into at the greater detail to see what are the properties that a component should have in order to have the improved functionality and the life. But here in we will be focusing on the processes need to be used for processes which are available for surface modification. So now we will be going for the surface modification through the processes where there is no change in chemical composition. So surface modification without chemical composition change. So as I have said, this set of the processes, there are set of the processes which work on the three approaches. One is transformation hardening, second is the grain refinement, and third is the work hardening. And there are various processes under these categories. In transformation hardening we have like flame hardening, induction hardening, laser hardening, and the plasma arc hardening. The grain refinement using the like laser melting or the TIG melting can be used. TIG or PAW melting can be used for refining the grain structure, especially of the substrates having the coarser grain structure. And on the processes which work on the work hardening, where near surface layers are deformed plastically, so that the work hardening facilitates the improvement in strength and hardness, and so the wear resistance. And this is normally applied. The methods are like burnishing, shot peening, friction stir processing. These are some of the methods which are used in this category. So we will be talking the basic principles of the transformation hardening first, and then grain refinement, and then deformation based approaches. So the first is the transformation hardening based processes. Transformation hardening based processes, wherein either these are thermal methods, whether either laser or the flame or induction heating or a plasma arc is used. In all these cases one common principle is used. This is basically applied for medium and high carbon steels, or the steels having the good hardenability. So normally it is applicable for the steels having the percentage carbon greater than 0.3. Why it is so? Because if the carbon steel is having more than 0.3% carbon, then it will show the good hardenability and increased tendency for the martensitic transformation, so that required hardening can be. Only difference is in the source of the heat. Source of the heat may be laser, may be flame, may be plasma arc or induction of the current. So in this one, what is exploited basically, like say this is the triple T diagram or CCT diagram for 0.3% carbon steel, and this is the critical cooling rate. So what is done basically, this is the transformation zone, this is MS and this is MF, and this is the austenitic zone. So what is done, the component having the like say 0.4% carbon steel, when its surface is heated through the suitable source of the heat like laser or electron beam or the flame. So heating is done suitable in such a way that it gets heated up above 800 to 850 degrees centigrade. So homogeneous austenite near the surface layers is formed. So for this, for the flame or a electron beam or plasma or laser etc., anything can be used. And once this homogeneous austenite is formed, we will be using suitables either in case of the laser, in case of the electron beam, and also in case of mostly in case of the induction hardening. No additional source of the cooling is used, because the cooling conditions under these conditions are so fast that automatically austenite transforms into the martensite because of the high cooling rate experienced in these cases. So what we do basically, very thin layer is heated to the austenitic state, and since it is in very metallurgical contact and good thermal contact with the base material, so as soon as the heat source passes through, these zones will be experiencing the higher cooling rate from the austenitic zone and will be getting transformed into the martensite. So, for improved hardness and improved wear resistance, this is normally applied for cast iron and high carbon steels for the components like the crankshafts and other components which will be under the metal to metal contact wear conditions. So, this is the basic principle of the transformation hardening, wherein the rapid heating to the austenitic state followed by the rapid cooling either due to its own cooling effect or followed by the water cooling water quenching method, the martensitic transformation is realized. In flame hardening, wherein lot of heat is actually fed. So, basically there is a source of flame and it is applied onto the surface. So, once this, like say the flame is moving like this, then additionally we apply a jet of water, because flame will be applying lot of heat to the substrate. So, the depth up to which heat will be transferred will be greater, and the depth up to which the modification will be taking place, that will also be greater. So, automatically the base metal will not be able to provide the sufficient cooling rates to ensure that austenite to martensitic transformation takes place, and therefore we need external cooling. And for that, once the heat source has passed, so we will be applying the jet of the water, so that the zone which has been heated to the austenitic state can be quenched in order to have the suitable martensitic transformation. So, in this case basically the heating followed by the rapid cooling is facilitating the transformation from austenite to the martensite. And in those systems where even if there is no martensitic transformation, the grain refinement can also lead to the improvement in properties. So, like the low carbon steels and other like aluminum alloys which are not heat treatable, even if simply pass the heat source quickly, the region will be heated to the austenitic state and followed by rapid cooling will result in the fine grain structure at the surface, and that will also lead to the improvement. But for these systems wherein like low carbon steel and cast aluminum alloys which are not heat treatable, basically work hardening methods are used. In work hardening methods, in addition to the work hardening methods, just for grain refinement structure, what we can do, we can apply intense heat source, so the surface layer melts, followed by the rapid cooling due to the thin layer, since the thin layer is layer which is being melted is very thin, so it is immediately quenched by the underlying base material, experiences high cooling rate, and that in turn leads to the fine grain structure, because high cooling rate, if the cooling rate is really high, then it will be leading to the increased nucleation rate and reduced growth rate. So, whenever this combination is present, we find very fine grain size in the metal, and that is why the TIG melting of the aluminum, cast aluminum alloys, and the laser melting of the steels leads to the very refined grain structure. Work hardening methods are applied for those systems which do not respond very effectively to the heat treatment or thermal methods. In those cases, basically near surface layers are deformed intentionally plastically, so that the work hardening can be facilitated. We know that if the material is having few dislocations, it will be softer, it will be of the lower yield strength. But if it is subjected to the severe plastic deformation, it will be leading to the development of the large number of dislocations here and there, and that in turn will be leading to the increased hardness, increased yield strength, and improved mechanical properties. So, this concept is applied or exploited in the surface modification also, wherein either two approaches. One, either we do burnishing or we do shot blasting or we do FSP, friction stir processing. in all these methods basically the surface layers are modified. So, intense plastic deformation of the near surface layer by the frictionist processing will be leading to the increased hardness and increased strength due to the work hardening. This is one thing which is which happens in case of the FSP, but if it is the short blasting, in case of the short blasting like high speed balls like this are directed onto the surface, like balls like 5 to 10 mm diameter of the steel balls of 5 to 10 mm diameter moving at 100 meter per speed, 100 meter per second speed directed onto the surface. So, whenever these balls strike to the surface gets locally deformed plastically, means the near surface layers get plastically deformed, and this will be causing the work hardening as well as the development of the compressive residual stresses. Because here if we see, if just surface layers have got deformed, so this region will be under the plastic deformation, but region below that will be under the plastic deformation. Will be under the elastic deformation. So, this elastic deformation will always try to bring the material at the surface in its original position, and because of that it sets in the residual compressive stresses, and that is why short blasting, varnishing and the contour rolling etc., they tend to develop the residual compressive stresses as well as they cause work hardening, and therefore the improvement in hardness, yield strength and development of the residual compressive stresses, these in turn increase the tensile strength of the material, these improve the fatigue strength of the material, and these are very favorable. It has been reported that like a 20 to 30% improvement in the fatigue life can be achieved through the mechanical working based methods in very controlled way, so that the surface layers are deformed plastically in controlled way, residual compressive stresses are developed, surface gets hardened and strengthened, which in turn resists the plastic deformation, nucleation and growth of the crack required for the fatigue failure of the component. So, now here I will summarize this presentation. In this presentation basically I have talked about category of the methods wherein there is no need of the change in composition of the surface layers, simply by the transformation hardening or grain refinement or work hardening approaches, the surface layers can be enhanced in terms of the mechanical properties for improved performance and improved life of the component. Thank you for your attention.